Welcome to my interface. I am the Advanced Learning Facilitation Entity, or A.L.F.E for short. I can assist you to understand advanced topics in science and facilitate you to learn how complex materials and chemicals work. Graphene is a solid comprised of covalently bound atoms of the element carbon. Certainly, let's start with the basics. This will explain the concept of an atom. Everything around us, in the world, in the universe, every single thing is made up of small building blocks, or units called atoms. Take this metal cube, for example. We can cut it into smaller and smaller pieces. If we divide the cube like this around 20 more times, we would find that we cannot split it any further. These indivisible parts are called the atoms. The name comes from the ancient Greek atomos, which literally means indivisible or uncuttable. We now know that the atom can actually be subdivided into smaller parts called protons, neutrons, and electrons. However, to understand many real-world processes or phenomena, it is enough to think of them approximately as spheres. We call this the hard sphere model. Next, consider the different elements including carbon. Everything in the universe is comprised of atoms, each consisting of 3 subatomic particles known as protons, neutrons, and electrons. Protons and neutrons are found in the nucleus at the center, while the electrons move in a region around the nucleus known as the orbital. The number of protons in the nucleus can vary, with the simplest case being a nucleus containing just one proton. Typically, the number of electrons matches the number of protons, and this is referred to as the ground or neutral state. The number of neutrons can differ, and atoms with the same number of protons but different quantities of neutrons are called isotopes. The properties and behaviors of the atoms are influenced by the number of protons in the nucleus, each configuration representing a distinct element. For example, the element hydrogen possesses 1 proton, helium has 2, lithium contains 3, and so forth. The periodic table of elements systematically lists all known elements based on increasing number of protons. It is periodic because elements with similar properties and behaviors are grouped together. Finally, it is necessary to understand chemical bonds. In nature, elements are seldom found in isolation as individual, uniform atoms. Instead, they combine to form compounds referred to as molecules. For instance, the air we breathe contains oxygen and nitrogen, which exist in pairs, 2 oxygen atoms bound together and 2 nitrogen atoms bound together. Water consists of 2 hydrogen atoms bonded to 1 oxygen atom, while sand is roughly composed of 2 oxygen atoms bonded to 1 silicon atom. Various types of bonds secure the atoms together. In a covalent bond, electrons are shared nearly equally between the participating atoms, as seen for oxygen and nitrogen. In other cases, some atoms may completely strip the electrons away from the other atoms. For example, when sodium bonds with chlorine to make table salt. There are also bonds which arise from the interaction between molecules, known as van der Waals forces. The strongest of these are known as hydrogen bonds, which occur when hydrogen links with certain elements like fluorine, causing a very uneven sharing of electrons. Metals have an interesting bond structure where the metal nuclei are bound together by an ocean of free-moving electrons, holding them together like glue. It is a phase of matter that depends on its temperature. Of course, first let's look at temperature. Objects in the world can sometimes feel hot or cold to the touch. This is because these objects contain different amounts of energy. The energy will flow naturally from the hotter object to the cooler one. The energy causes the atoms in the object to move about. They can spin around, jiggle, or vibrate randomly, and even zoom off in every direction. It is useful to measure the amount of energy, and we do this using a temperature scale like kelvins. 0 degrees on the Kelvin scale, also known as absolute zero, is the temperature where the object has zero energy. This means the atoms are perfectly still, with no motion whatsoever. Temperature was originally defined according to easily observable events or transitions, like the melting of ice and boiling of water. Over the years, many different scales have been used. These are all equivalent, but with different values at the observations. Next, we can define the phases. Solids can be found everywhere, like rocks, snow, and trees, to name a few. Another common phase of matter is liquids, such as the ocean, milk, or oil. We are also surrounded by gases like the air and wind, helium in balloons, or the butane used for cooking. The atoms or molecules around us are also referred to as matter. The phase or state of matter depends on its temperature. For instance, below 0 degrees Celsius, water exists as solid ice. Between 0 and 100 degrees, it turns into liquid water, and above 100 degrees centigrade, it forms a gas known as water vapor or steam. At low temperatures, water molecules possess less energy, vibrating minimally and remaining fixed in place as a solid. With an increase in temperature, they gain energy, moving more vigorously and eventually separating to move more freely. This explains why a liquid can flow and fill a container. If we raise the temperature high enough, the atoms or molecules have enough energy to break free and fly off, becoming a gas like steam. There are many other states of matter that arise under special conditions, like a plasma at high voltages, or a Bose-Einstein condensate at absolute zero. Here is more information on metals. A metal is a collection of atoms from a specific group of elements with similar properties. Examples include iron, used in the construction of cars and buildings, gold, employed in jewelry, and aluminum, used to make soft drink cans. Metals exhibit a distinctive bond structure where the atoms are held together by a sea of electrons, acting like a glue that holds them in place. This unique structure gives metals some very useful properties. The free electrons mean that they can easily conduct electricity, so they are found in power cables and all electronic devices. Furthermore, metals demonstrate high malleability, meaning they can be easily shaped into practical forms such as sheets, wires, and pipes. They can also be readily forged or molded into more complex shapes. Metals stand out as one of the most indispensable materials, playing a vital role in shaping our modern world. I can explain the concept of conduction. Heat is the energy contained in matter which can move from high to low temperature. One way by which the energy moves is known as conduction. If a metal sheet's edge is heated, the entire plate gradually warms through this process. As heat is added to the atoms at the edge by the flame, they begin to vibrate and move more rapidly. This causes them to bump into their nearest neighbors, transferring some of this energy to them, making them vibrate more. These then collide with their neighbors, and so on. Eventually, the heat energy is transferred through the whole plate, which we can measure as a rise in its temperature. Some of the best conductors of heat are the metals copper and silver. This means the opposite end of a silver spoon will become hotter much faster than a wooden spoon. There are also other ways in which heat energy can be transferred, such as convection and radiation. Due to its covalent bonds and two-dimensional structure, it can rapidly transfer heat. The following will explain dimensionality. Objects in the world take up space and possess a specific volume, like buildings, a lake, or an apple. To determine their volume, we need to measure their dimensions. For simple objects like a cube, this means finding its length, width, and height. Because these objects have 3 dimensions, they are referred to as three-dimensional. Some objects are very thin, like a sheet of paper or metal. Their height is a small number, so they occupy a very small volume. But their length and width can be big, so they can occupy a large area or surface, resembling a flat plane. These flat objects are referred to as two-dimensional since we can neglect their height. In certain cases, an object can be very flat and very thin, like a pipe or a wire. These shapes can be considered as one-dimensional. To refer to these dimensions in a more general sense, we call them axes. By convention, these are labeled as the X, Y, and Z axes. Allow me to demonstrate. Graphene is comprised of the element carbon, which has 6 protons and electrons. The carbon atoms form the strongest type of bond. In this covalent bond, the electrons are shared equally. However, in graphene, carbon has a double covalent bond, making it even stronger. With these bonds, the atoms form a 6-sided hexagon. These hexagons are further linked together to form a honeycomb structure. Furthermore, these bonds are only two-dimensional, meaning graphene is extremely thin. In fact, graphene is only 1 atom thick, or around 100,000 times thinner than a hair. This makes graphene extremely light and strong. If you could pull on a fiber made of graphene, it would be 500 times stronger than a steel wire of the same size, but it would weigh 3 times less. Unfortunately, graphene is very difficult to make, but in the future, it could be used to make amazing structures such as an elevator that reaches into space. Bringing together all the concepts covered, it can be explained as follows. When atoms heat up, their vibrations are transferred to the atoms around them, but this depends on the strength of the bonds between them. Imagine 4 metal balls, 2 interconnected by a rubber band and 2 joined by a metal rod. If one ball is moved around, the other ball connected by the rubber band will not move much as the rubber stretches. However, the ball linked by the stiff rod will immediately move with the other ball. In a similar way, when atoms with a strong bond vibrate, nearby atoms will almost immediately start to do the same. Furthermore, if an atom is surrounded by other atoms in 3 dimensions, its energy will be split between all 3 directions equally. However, if an atom only has neighbors in 2 directions, all the energy is transferred to fewer neighbors, intensifying the effect. Graphene has both very strong bonds and a 2-dimensional structure. This allows energy to be transferred along the atoms extremely rapidly, making it the best conductor of heat energy that is currently known. I am the